Anyway, okay, so we ended here with if you reject the null when you're doing the 6 steps, there's a significant correlation. If you fail to reject the null, there's not a significant correlation that you found in that data. So it might be there still is a significant correlation in the population, it's just you don't maybe have enough participants, or you just didn't find it in this experiment. What we didn't get into was effect sizes and confidence intervals. So R is an effect size. We kind of talked about that. The rules are 0.1, 0.3, and 0.5. A lot of people will just square it so that they get the same thing as the last chapter we did, ANOVA. You can also convert R to Cohen's D, but people are moving away from that because we're trying to match the effect size to the design type. And so to change everything to a effect size that matches a groups design implies that it was groups even if it wasn't. So a lot of people just use R as effect size because then you don't have to do any extra work as well. Okay. Now confidence intervals are a disaster. So if I was doing them by hand, it would involve what's called a Fisher's R to Z. We talked about at the very beginning the formula for R is a version of z-scores, right? So x minus the mean over standard deviation is the z. So it's the cross products of the z-scores. So what you do for confidence intervals is transform them back to z, do some math, transform them back to R. It's awful. It's like talking to somebody who does everything in Celsius, and they're like, you can say, oh, it was like 80 yesterday. And you can see their little brain being like, what? And I'm like, wait, sorry. It was like 30, 25. You're fine, sorry. I forgot. And then so they're calculating back and you're calculating forward and everybody's just confused. Right? So most people don't do that. But remember that core.test, the output from the R output gives it to you right here. So that does make it a little easier because it's just right there. So if you ask for a confidence interval, you can pull it from that. I don't even think they're in the book because they're kind of a pain. And then the last couple little slides are about just why correlations. So we started with a list of all the problems. There are outliers, restriction or range, directionality, and the third variable problems. A lot of people use these correlations because it seems like a pain. Right? And that's really where psychometrics comes in. So if you ask me what I did when it comes to statistics, I would say that I do psychometrics. Okay? My specialty is scale development. So we look at the development of tests and measures. Like, how do scales work? Do they work the way we think they work? Are they consistent? Are they consistent across groups? So I work a lot with one of my friends who does meaning in life to ask that question about his scales. And really what we'll do is we'll look at reliability and validity. We get into stuff that's more complicated than correlation, but it's all based on the same idea of correlation. So reliability, there's like 27 different types, but the main two are test, retest. So that's something you should be familiar with. You take the test once, take it again, you should get the same score. So standardized testing, they work really hard to make sure that the scores are reliable. That's why I always tell people don't take the GRE twice. It's not worth your time. It's very reliable. Unless you're violently ill during the first one. Then all bets are off. Same with the LSAT, the MCAT, SAT, ACT, your scores are going to stay consistent. Split half reliability is if you don't want to test people twice, you can take a big data set, split it in half, and make sure the reliability is matched for both halves. Generally what you'll do to get those numbers is Cronbach's alpha. Sometimes it's called coefficient alpha. And that is a correlation of how, that says alpha.
Alpaca.
I should say alpha. I was like, what? Something looks wrong here. Alpha, which is unrelated to type 1 error. Okay, so we've used the same names again, unfortunately, but it's not the 0.05 thing. So for Cronbach's, for test retest, it's a correlation between time 1 and time 2. For split half, it's kind of an average of all the correlations of the questions. And you want that to be bigger than 0.8. So you want your reliability to be very large. And so think about that as like kind of how much that's going to give you the same score each time. Validity is the flip half. So plenty of scales can be reliable that are not valid. So you can get the same score over and over again, but it won't be a score that means what you think it means. This is harder to test. This idea of like, how do I get at what is it measuring what I've designed it to measure? Because in psychology, we're often talking about things that you can't see. So if you're measuring metacognition, for example, so those surveys you take for each test, like I ask you a question about that, but I can't literally see you thinking. So it's harder to measure. So we'll still use correlation to calculate validity, but we'll take a measure and correlate it with something that we already know measures that. So if we were developing a new meaning scale, I would be able to measure it against other meaning scales that people have validated. Or, conversely, make sure it correlates with things it should correlate with. So it should correlate pretty negatively with depression. So that's using existing research to show that this new thing still works correctly. And so I spend way too much time on BuzzFeed. If you ever are on BuzzFeed, so many of those ridiculous answer these personality questions, and they're just silly. We could, in essence, use those correlation to validate, not those because they're silly, but a personality test. So there are tons of personality scales. There's the Big Five. There's just so many. It's just out of control, right? MMPI. And it's a way to establish validity. So it's much harder to do than reliability because we have to agree that using this metric means that this scale also matches. Right? And so anytime people send me that Myers-Briggs stuff, I'm just like, right? Because it's a perfectly reliable scale. Validity question. So I'll pick on BuzzFeed because they have tons of these scales that are just ridiculously not valid. And the last thing we're going to cover is partial correlation. So one of the biggest problems, so we talked about restriction of range. We fixed that by having a good study. We talked about outliers. We looked at scatter plots to see if we have outliers. And then we talked about the third variable issue. Directionality, the only solution is to run a true experiment. So I think we mentioned, what was it, ice cream and
Drowning.
Drowning? Yeah, okay. I was like, is it drowning? There's
Also shark attacks.
yeah, there's a couple examples first on this one. And we said that they're highly related. What really is causing that is heat. I could draw as well. So outside temperature. So partial correlation allows us to figure out how much of these two variables, ice cream and drowning, are still related after removing a third variable. So this is a way to test the third variable problem. So it takes time correlation, IV1 on our x and y, right? It removes z, the third variable, and it tells me how much is left between x and y. So to give you a real example, we were testing how much people's grades improved by going to supplemental instruction, or the PASS program here. Obviously highly correlated with GPA, right? Because smart kids are going to do better, and smart kids are more likely to go. So we did a partial correlation and took out the effect of previous GPA, so as a measure of aptitude, and we're still able to show that if you went to sessions, your grade increased. Otherwise, the argument is that has nothing to do with sessions, it has everything to do with previous performance. And so that's kind of what it looks like. So if we look at the correlation, their example that was funny yesterday, absences in exam grade over homework, excluding homework. So if I looked at exam grade and absences, it would be A and B. But then if I say, well, some of that has to do with homework, it would take B out. So we would get the correlation between exams and absences, just A, without having B in there. And in this example, there would be no relationship between ice cream and drowning. It would be all due to heat.